Once again, welcome back to the course, and here today we'll talk about virtual memory. The main purpose of the concept of virtual memory is to give each process in the operating system sense the illusion of a large private address space that any other process in the system is not able to infringe on. Historically, it was also a way to provide the ability to run programs that were larger than the available physical memory through demand paging. However, the price to these benefits is the need to perform an address translation on each memory reference. Address translation is done using two mechanisms: a page table which holds the address translations and a translation look-aside buffer, which is a cache which holds the most common page table entries. This slide illustrates the concept of page tables. Just like the address space is divided into blocks for cache memories, in virtual memory the same concept is called pages. The physical memory contains page frames, which each can hold a virtual page. The hierarchical page table, as shown here, is a common way of organizing page tables and is used both in x86-64 and RISC-V processors. The page tables are structures stored in the physical memory managed by the operating system. In the illustration, the page table is divided into two levels. First, we have a register in the processor that holds the pointer to the level 1 page table. This system register will be replaced when there is a context switch to another process, which will have its own separate address space. The level 1 page table is indexed with a part of the virtual address P1 to get a pointer to the level 2 page table. Then another field in the address P2 is used to find a page table entry. The page table entry, or PTE, contains the information about permissions, for instance execute, read or write, and whether or not the page is present in physical memory, or if it needs to be fetched from secondary storage, that is, the disk. If the page is in memory, the PTE contains the final page address, which then is concatenated with the page offset to form a physical address, and the memory reference can take place. This lucky situation will take 10 to 200 clock cycles as it involves multiple memory accesses. If the page is not in memory, the PTE contains information on where it can be retrieved from disk, and an I/O operation is initiated to retrieve it from disk. This is called a page fault, and is such a lengthy operation, on the order of milliseconds, that it's not meaningful to wait, so instead the operating system marks the process as blocked and switches to another process. In the figure on this slide, checked entries in the page tables represent unallocated memory. The multi-level page table structure significantly saves memory space for page tables, as holes in the address space with unallocated memory do not need page table representation as it would have in a single level table. Since the page table needs to be consulted on every memory reference, including instruction fetches, it would be infeasible to form from a performance perspective with virtual memory unless we can speed up address translation considerably. Luckily, we can do that with a TLB. This is a way how we could integrate virtual memory support in the regular pipeline. We have separate instruction and data caches so that we avoid the structural hazard when we need to fetch an instruction at the same time a data memory access is needed. In front of the caches we have a translation look-aside buffer, a TLB. The TLB is a cache and can be organized in the same way as regular caches, except it does not contain blocks of data but page table entries, PTEs. If we hit in the TLB and there is no protection violation, for instance trying to execute from a data page, everything is good. If we miss in the TLB, there is a hardware page table walker that performs the lookup in the multi-level page table as described previously. If the page is in memory, the page table entry is sent back to the cached by the TLB. In the event of a protection violation, this is signaled as an exception to the operating system. In case the page does not exist in memory, a page fault is generated and will also transfer control to the operating system. This image summarizes the whole address translation process. So first we have a virtual address. We do a TLB lookup. This is a hardware structure. If we have a hit, we make a protection check. If the operation is permitted, we send the address to the cache. If it's denied, we take a protection fault, a seg fault. If we miss in the TLB, we look in the page table to find the address. This can be both done in hardware or in software. If the page is in memory, we update the TLB and restart the instruction, which will have to do a TLB lookup again. If we miss, that is a page fault, then we transfer the situation to the process to the operating system, which will handle the page fault and then restart the instruction. Virtual memory requires that we talk about exceptions. An exception is like an interrupt, but is generated by events inside the processor itself. It's a signal of some error that needs to be handled. When you experience an exception, you abort execution, transfer control to an operating system function that handles the exception, and then, depending on the exception, you return back to the code and continue execution, or abort the process, that is, crash. TLB misses can be implemented in hardware or in software. If it's handled in hardware, the processor just waits. If it's in software, an exception transfers control to an operating system function and the instruction is retried at return. Page faults also need a restartable exception like TLB misses, handled by software. It's preferred to use precise exceptions. A precise exception is characterized by that the state of all instructions that are in program order before the faulting instruction complete, and that no instructions after the faulting instruction have had any effect on state. This is relatively easy to achieve in the 5-stage pipeline, as all instructions issue and execute in order. Protection violations is an exception which often crashes the program. Page faults is a type of exception that you should recover from, so you need to be able to restart and re-execute the instruction that caused the fault after having fetched it. With virtual memory, you need to add address translation before being able to access the caches that work with physical addresses. We need to cope with additional latency of the TLB. What are our options? We could slow down the clock cycle. This is not really a solution, as it would penalize all instructions. Could it be possible to pipeline TLB and cache accesses? Yes, this is a common solution, but it increases the pipeline depth, which has consequences for data hazards. What about possibility to make a parallel TLB and cache access? Yes, that is also a very common solution. Let's see how that works. This figure illustrates the last option, having a concurrent access to the TLB and cache. This is done by putting some restrictions on the page size compared to the number of sets in the cache. If the number of sets is small enough, the index can be taken from the page offset in the address, which is not affected by the address translation. Therefore, this is used to index the cache. However, the address tag in the cache is still the physical address, so when comparing the tags, the physical address needs to be used. The TLB is normally a much smaller cache than even the L1 cache, and therefore is ready with the translation where the address tag check is done. The constraint is that the number of bits needed to index the cache, capital L, plus the bits for the block offset B must not be larger than the bits for the page offset K. So the third option does not work. To round off, support for full demand page virtual memory is very common nowadays. It simplifies so many things that it's not worth being without it. That said, small embedded processors usually have only physical addressing and is quite happy with that.